Hi, everybody, and welcome back. In this lecture, we're going to talk about the foundations of statistical inference. Inferential statistics are all about drawing conclusions from a sample about a population, or to see if we have some form of meaningful differences between our variables. So we'll start with that. And then in terms of calculations, I'm going to talk to you about how to calculate standard error of the mean. And I'm going to talk to you about how to calculate a z-score for a sample. Those are the two formulas that are relevant. So here we go. So you might ask yourself, why inferential statistics? Right? Why can't we just get away with summarizing the results? The truth is, without being able to apply inferential statistics, we would not be able to make any meaningful conclusions about our data set. So typically, when we collect data, we use a sample. And you may recall from an earlier lesson that a sample is referred to as a subset. Sorry, my cat's coming into view. A sample is a subset of scores or a subset of the population, whereas a population is all parties of interest. So if you're trying to draw meaningful conclusions about the population, but you have a sample, you might need to use inferential statistics, because here's the deal. Without doing this, it's possible that our sample is atypical. It's possible that the results could be discredited at a later point in time. And this idea of inability to reproduce a finding can be a problem for your results, but it's a problem for all behavioral sciences, not just psychology. So when we do inferential statistics, we really have three goals. One is to guess point estimate or population parameters. So we, given a given sample mean and variance, we could estimate the mean and variance of its parent population. So that could be useful. We can also determine interval estimates or confidence intervals, which is a range of values that the population score likely falls into. So for example, if I had a score of 60 plus or minus 6, that would mean that in all likelihood, the population score falls between the range of 54 and 66. That's 6 points below and 6 points above whatever our sample mean is. So that's good. And in terms of surveys, you always see them state their confidence interval, and interval estimates is very important. And then obviously we want to know how to draw meaningful conclusions, right? All right. So previously, when we think about z-scores, we were interested in individual scores, right? And even with the z-scores, we said x minus x bar, x minus mu, we're comparing an individual score relative to a reference group, the mean of that reference group, right? But from this point forward, we're only interested in group differences or group similarities, right? So we're shifting away from individual scores to group scores. Now, we still need to measure central tendency. And if we're relying on a normal distribution, the mean and standard deviation are the typical scores that we use. And sure enough, if we look at inferential statistics, we tend to look at means, variances, and standard deviation for one formula or another. Okay, so let's try and figure this out, right? So if we wanted to know whether our sample was, significantly different from our population, we would then have to, know the population mean, know the population standard deviation for height. So the reality is that if we had an individual sample, we could compare that relative to the population mean of 68 inches and a population standard deviation of 3.2 inches, right? So the truth is, we could also do a whole host of distributions like we talked about. Really, the bell curve is a whole bunch of normal distributions. And then the average of all the distributions is usually what the population mean and standard deviation land on. So if we were to take the height of every man in our sample, and we had 100 people in our sample, and we did the same thing for 1,000 samples, let's say, we would get a shape that looks like a normal distribution. So there are assumptions here about the normal distribution or the population being shaped in a bell-shaped curve. Now, central limit theorem suggests that as the size of your sample increases, your means and standard deviations are going to get closer and closer to the population mean and standard deviation. So as sample size increases, your means are going to match the population mean a little more, and your standard deviations are going to match your population standard deviations a little more. But we acknowledge that all samples are conservative estimates of the population. So as soon as we're dealing with a sample, there is some level of error involved, right? So what do we recommend if we wanted to reflect a normal distribution? Well, different researchers say different things, but in your book, we say we need an N or a sample size of 30 to 40 people before you get that. If you read the book from Cosby and Bates, they say 20 to 30, and there are other people who say 50. So I'm okay with your book saying 30 to 40 because that's somewhere in the middle. Now, so at that point, it would come as no surprise if we did those 1,000 samples and took the average of 1,000 samples of 100 people, that the mean height would be 68 inches, right? So that shouldn't shock you because the population mean was 68, right? So what's the point? The population normal distribution is actually a theoretical shape that reflects the totality of a whole bunch of smaller distributions within it. So if I may, I'm actually at home, so I don't have the college's blackboard. So I brought my own blackboard. So if I may, let's say I had a normal distribution, right? So you see that bell-shaped curve? Really, that bell-shaped curve is a bunch of other bell-shaped curves along the way. And then if we were to average all of these bell-shaped curves for sample one, S1, S2, S3, S4, S5, S6. So we had 6 samples here. Now, the more samples we do, the more it's going to approximate a normal distribution from the population angle. But if we were to average all of these smaller samples, it would come up to our theoretical population distribution. All right. So I'm going to erase that, but that's basically what central limit theorem suggests. Central limit theorem suggests a couple things. The first is that as sample size increases, it approximates the population more and more. And then if you took 1,000 samples and average them, it would bring you to your population distribution. So, but as long as we're dealing with a sample, we have to calculate standard error of the mean. So samples are conservative estimates of a population, and we acknowledge that all distributions have some error, right? So the formula for standard error of the mean is the population standard deviation divided by the square root of your sample size. So if you have smaller standard deviations or larger sample sizes, that's going to reduce your standard error of the mean, right? So that's very important. There are two things. In the numerator, the smaller the population standard deviation, the smaller your standard error of the mean is going to be. And in the denominator, the larger your sample size is, the smaller your standard error of the mean is going to be. All right, so here is the formula for a z-score for a sample. Now, to calculate a z-score for a sample, you have to know the sample mean, the population mean, and the standard error of the mean. So there are really three parts, right? So X bar is the symbol for sample mean, and mu is the symbol for population mean, and standard error of the mean is our denominator. So we could actually calculate this and figure out what our probabilities are. So what I'm going to do is I'm going to write it down and we're going to go through it together. So we have a population mean of 99 pounds, a sample mean of 98 pounds, a sample size of 25, and a population standard deviation of 4 pounds. So what I'm going to do is I'm actually going to take this slide off so that you can actually see the board bigger. But here is the question. Suppose we know the average weight of 6th grade boys is normally distributed with a population mean of 99 pounds and a population standard deviation of 4 pounds. What is the probability of getting a sample of 98 pounds or less, right? So now you may recall from the previous lesson, we actually have to calculate where it is above or below. Less would be below. So we'll plot this on the bell curve too. So let me stop my share and set this up on the board, and we'll go from there. Give me 1 second. Okay, so here we are, and I'm sorry for the angle. I'm not at my my desk at the college, so forgive me for that. We have our population mean, 99 pounds. Our sample mean, 98 pounds. Our sample size of 25. And our population standard deviation of 4. So the formula for a z-score for a sample is going to be sample mean minus population mean. Sorry, my cat wants to make an appearance. Sample mean minus population mean divided by standard error of the mean. So let's work through this together. So the first thing we're going to do is we're going to put our numbers on the board. So X bar, 98, right? That's our sample mean. Mu is 99. 98 divided by 99 is our numerator, divided by the standard error of the mean, right? So standard error of the mean, we have to calculate, but our standard deviation was 4, and our sample size was 25, right? So I put my standard error of the mean here. Now, my advice is when you're doing it, calculate the standard error of the mean first. So 4 divided by 5 gives me 0.8. And I can bring 98 minus 99 across. So that's -1, right? 98 minus 99 is -1. And -1 divided by 0.8 gives us what? So it gives us -1.25, right? So if we do that math, that would be our z-score for a sample. Now, we asked a question, though, what is the probability of getting a score, right, of 98 or less, right? So now we still have to go to the back of our book to figure out, well, what is this z-score of -1.25? So I'm going to go back to the back of my book, go to my z-score table, and I'm about to tell you what the answer is, if you give me a second. So in this, which is an older version of the book, we're looking for table B. In a newer version of this book, you're looking for table A. So I'm going to go down to 1.2 and then across to 5. 1.25 gives me 39.44, right? That's a z-score of 1.25, 39.44%. So 39.44, and I need to know what's left over of the 50. So we do 50 minus 39.44, and that gives us an answer of 10.56%. So the probability of getting a sample where the kid's weight was 98 pounds and the population was 99 pounds with that sample size is 10.56% or lower. Good. So let's go back into our slides and do the next one. So the next one said that we have a beveraging company that set their bottling machinery to a population mean of 16.5 ounces. So I'm going to erase this and I'm going to modify these 4 numbers, but it's going to be the same process. So the population mean was 16.5, right? So we have that with a population standard deviation of 0.5 ounces, right? Then we have iced tea being sold in 6-packs, right? So we assume that each of the bottles in a 6-pack is a random sample. So what is the probability of getting a mean bottle amount of 17 ounces or more? So, and we have 6-pack, right? So our N is 6, right? So what I'm going to do is I'm going to do what I did before so that you can see it bigger, is I'm going to stop my share and I'm going to keep the formula up, but I'm going to mess around with the numbers. Okay. So here we are. Again, the question was, We had a population which had 16.5 ounces in bottle, a sample mean of 17. We want to know a sample with 17 ounces or greater, a sample size of 6, and a population standard deviation of 1/2 ounce. What I'm going to do is I actually do need to get my calculator or my phone that I dub as a calculator, and I will be right back. All right, so we're back. Again, we need to calculate the z-score for a sample mean minus the population mean divided by standard error of the mean. No problem. So here's what we do. We say we want to find 17 ounces or greater. So we're going to do 17 minus 16.5 divided by our standard error of the mean, which is 0.5 over the square root of 6. So here we go. Remember I said calculate the bottom first. Now I needed my calculator because I don't know the square root of 6 offhand. So what we do, and I'm going to clear this, I'm going to press 6. If you turn the calculator around, you'll see sort of like a check mark. Let me find it first, where it says here, the check mark where it says 2 check mark X, that'll be a square root. And then when you do that, you get 2.449. So that is going to be 0.5 divided by 2.449, right? And by the way, this is just the denominator we're calculating because we calculate the standard error of the mean first. So we do 0.5 divided by 2.449, and that gives us 0.204. So our denominator is going to be 0.204. Our numerator, we still didn't carry across, right? 17 minus 16.5 is 0.5. So what is 0.5 divided by 0.204? So we'll do that and we'll calculate that. The z-score for the sample is going to be 2.4509. So we're just going to do z equals 2.45. So that calculates the z-score for a sample. But as we keep saying, you still have to use your z-score table, right? So I have to go in the back of the book and find 2.45. Okay. So I go down to 2.4, cross the 5, it's 49.29. That's where that is, if you look at it. So no problem, 49.29. So I'm going to do my bell-shaped curve. And here is my 16.5, right? That was the population mean. And I wanted to know what the likelihood of getting 17 or higher is, right? So this is the area that I need to figure out. Well, if there's 49.29% between the mean and that z-score, what's left over from 50? Well, we do 50 minus 49.29, and we're going to get 0.71%. So the probability of a bottling company making an error of even 1/2 ounce of Snapple is less than 1%, right? So it's 0.71%. Good. So that really is how you calculate z-score for a sample. you need to know the standard error of the mean, which is population standard deviation, and the sample size, which is n. You take the square root of that, that's your denominator. And then just like before, it's x bar minus mu. So let's stop this again. And then I'm going to go back into the slideshow. Okay, so if you notice, these two questions that I calculated were about the means, not individuals, right? So in the first one, we had population mean of 99 pounds, as you see my cursor, and the sample was 98 pounds, right? And then a population standard deviation and the sample size are there. And we said that was like roughly 10% and change. With the bottling company, it was 0.71%, right? So the probability of getting, bottles of 17 ounces or more when the machinery is set to 16.5 is very unlikely. So what does that tell you? Packing machinery for businesses are pretty strong. So, so far, we have demonstrated how to calculate a z-score for a sample. Now I want to talk to you about null hypothesis testing. When we talk about null hypothesis testing, we are trying to determine whether we have meaningful differences or not. So the null hypothesis says there are no statistically significant differences between the groups. And if there are differences between the groups, it's due to error, due to chance. Whereas the alternative hypothesis, also referred to as the research hypothesis, says no, there are meaningful differences between the groups and it's due to our manipulation, right? So that's the null and alternative hypothesis, right? So if we were to test whether, our sample with an IQ of 103 was significantly different than a population IQ of 100, we could do a z-score for a sample. But the null hypothesis would say that the average is equal to 100, right? There are no differences between the sample mean and the population mean. So that's what that would say, right? Whereas the alternative hypothesis would say, no, they're not one in the same. Okay. So whenever we do null hypothesis testing, we start with the assumption that the null hypothesis is true until proven otherwise, right? And so we're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. So the reason why we start with the null hypothesis being true is that if we say there's no difference between a group, can we calculate differences from a number called 0? Sure. What if we said the null hypothesis was false, right? Where we're saying there are real differences between a group. How do you calculate differences from an unknown? So we start with the assumption that there are no differences between the group until proven otherwise, right? Now, we can make a mistake. Based on our numbers, if the probability of getting these results are low, usually our probability or our alpha, right, is 0.05. Science allows you up to 5% error. So if the probability of getting this score is 5% or less, then we're going to make the leap of faith that there are real differences going on between the groups, and we're going to reject the null. So a type 1 error was when we made a mistake, we rejected the null, but we should not have. So a type 1 error is when we reject the null hypothesis, but the null hypothesis was actually true. So we said there are real differences going on when nothing was really different about the two. So, we could also make a type 2 error. A type 2 error is when we say there are no differences between a group, but there really are meaningful differences. So we could actually make a type 1 or a type 2 error. Now, when we analyze the results, we are going to analyze the results against probability. So we are always going to compare against a critical value and see if our results are higher than that critical value, right? So if we wanted to know if our IQ was significantly greater, this would be a one-tailed test, right? But when you don't know whether you should be assuming a one-tailed test or a two-tailed test, always assume two-tail. The standard is two-tail. In fact, SPSS, its default is two-tail. So critical values are in the back of the book, the score that needs to be met or exceeded to reject the null. So as it relates to z-scores, we need, I'll tell you, a score of 1.96 in the plus or minus as our critical value. So if our z-score is 1.96 or higher, we're going to reject the null. If it's less than 1.96 positive or negative, we're going to accept the null. So these are what we call critical value, the threshold. And anything beyond the critical value is what we call the area of rejection. If we had a one-tail test, right? So then we would need to get a score where 5% is on one tail, so we need a score of 45. So we would do 1.65. So in a one-tail test, the z-score that needs to be met or exceeded is 1.65. In a two-tail test, it's plus or minus 1.96. All right. So let's think about that for the time being. In a one-tail test, the critical value for a z-score was 1.65. That's a score that needs to be met or exceeded. When it's a two-tail test, the score that needs to be met or exceeded is 1.96. What does that do? Because we're splitting our 5% error across two tails, there's 2.5 on one side, 2.5 on the other, we have to get a higher number to reject the null. So the practical implication of having a one-tail test, smaller critical values are necessary to reject the null. That's the practical implication. And I talked to you about a type 1 and type 2 error. So let me plot this on our graph just to show you what I mean. And I'm gonna need a moment to erase, and then I'll come right back to you. Okay, so we're back again. And I left the standard error of the mean here. I left the z-score for a sample here for you to view. What I'm going to add are critical values. So a critical value was the score that needs to be met or exceeded to reject the null hypothesis. So the critical value for a two-tail is plus or minus 1.96. Right? This is two-tailed critical. That's a two-tailed z, whereas the critical value for a one-tail is 1.65 in one direction. It's not plus or minus. It has to be in the chosen direction. So just plus. In our case, right? So that's one tail. One tail. Okay. So we should be able to go through a series of steps. Now, the standard alpha is 0.05, right? So we want to see if we are going to reject the null. So we set a standard alpha of 0.05. So let's go through the logic of rejecting the null hypothesis. So step one, state your alpha. So alpha is 0.05. Step two, determine whether you have a one-tail or two-tail test, one or two-tail, right? And in our case, we're going to say, because we want to know if our IQ of 103.78 is significantly greater than the average, we're going to say ours is one tail. So the critical value, step three, would be to establish our critical value for a one-tail test is 1.65, 0.65. Step four would be to calculate our test. So if you humor me, I'm gonna do our z-score, right? Was 103.78 minus 100 divided by, I don't remember what the sample was. So let me pull that up. So we had, this was our question. We had 25 participants, right? And I'm glad I checked because it's 4.8, not 7.8, 103.48. And then we say 15 divided by 25. Okay. So let's calculate this, carry it across. We get 3.48 divided by 15 over the square root of 25, right? So 15 divided by 5 gives me 3. So 3.48 divided by 3. 3.48 divided by 3 gives me a z-score of 1.16. Now, let's go back. A critical value was 1.65. That's a score that needs to be met or exceeded. Is 1.16 equal to or greater than 1.65? The answer is no. So step 5 is going to be making a decision. So we're going to accept the null. Because 1.16 is not equal to or greater than 1.65, we accept the null and then we interpret it. If we accept the null, we say that our sample of IQ, 25 people at IQ of 103.48, were not significantly different than the population of 100. So, and then you're going to write that here. I don't have enough space. So we would say the sample, which had an IQ of 103.48, was not statistically significant than the population mean of IQ of 100. Did not meet or exceed the critical value. So that is pretty much how we do it. And then I'm going to go back. I'm actually going to make the screen bigger. So let me stop my share for the time being so you could see what I did. I realize that sometimes when I'm not in full screen, you can't fully see me. So the alpha 0.05, one tail, critical value, calculated the z. We compare the two. So 1.16 is not equal to or greater than a critical value. So we accept the null. And then we say there are no statistically significant differences between our sample, which had an IQ of 103.48, and the population IQ. Good? that is how you do it in a nutshell. And we're, believe it or not, almost to the finish line. So let's go finish out our slides and we can go from there. So what are the assumptions of the test? When we calculate a z-score for a sample, we assume that each individual in the sample were randomly and independently selected relative to the population. We also assume that the population has a normal distribution or a bell-shaped curve. These assumptions are important because if we violate these assumptions, then maybe we're not doing the right test. And that is our lecture, and I'm going to stop there.